Hey everyone, welcome back to the channel. I'm Darshan and today we're doing something special. We're building your first AI agent in Rust completely production ready from scratch. In my last video I explained why Rust is perfect for AI agents. Now, we're actually building one. And not a toy demo. A real research assistant that can search the web, analyze information, and give you intelligent summaries. By the end of this tutorial, you'll have a working AI agent that you can extend, customize, and deploy to production. Now, quick heads up before we dive in. I'm not going to write every single line of code from scratch in this video. That would take hours and honestly you'd get bored watching me type. Instead, I've already built the complete project using the Rig framework. The full code is on GitHub, link in the description. What I'm going to do is walk you through the architecture, explain how each piece works, show you the key patterns, and teach you the concepts so you understand exactly what's happening. Think of this as a guided tour through production Rust AI code, not a live coding session. You'll learn way more this way, trust me. Here's what you're getting in this tutorial: complete project structure for Rust AI agents, how to integrate the Rig framework with Ollama for local inference, building tools your agent can use, starting with web search, async workflows and error handling patterns, and production-ready code you can actually deploy. Whether you're a Rust beginner or experienced developer exploring AI, this is the most practical AI agent tutorial you'll find. Before we jump into the code, subscribe if you haven't already, smash that like button, and turn on notifications. I'm posting Rust and AI content weekly, and you don't want to miss what's coming next. Also, join our Discord community, link in the description. That's where we discuss code, debug issues, and share projects. The community is incredible, and if this content helps you, consider buying me a coffee. Every coffee funds more tutorials like this, link is below. Alright, let's build this agent. Before we look at any code, let's understand the mental model. This is crucial. An AI agent in Rust is made of three main pillars. First, we have the body, that's the CLI. This is how we talk to the agent. We'll use a library called clap to make a nice command line interface with flags, help text, and argument validation. Second, we have the brain, that's the agent itself. This is where the reasoning happens. We use the Rig framework to manage the conversation history, context window, and decision making. It talks to Ollama running locally on your machine. No cloud APIs, no costs, complete privacy. Third, we have the hands. Those are the tools. An AI without tools is just a chatbot. We're going to give it hands, specifically a web search tool so it can get real-time data from the internet. The AI decides when to use these tools on its own. That's what makes it an agent, not just a script. Let me show you the project structure. All free, done de that, de from. This is a standard Rust workspace layout. At the root, we have cargo, toml for dependencies, and project metadata, a .env example file for environment variable templates, and a README for documentation. Inside the source folder, we have 4 files. Main RS is the CLI entry point, the body, config. RS handles configuration management, agent RS contains the research agent, the brain, and tools RS has the web search tool, the hands, 4 Rust files. That's it. This is a fully functional AI agent in under 500 lines of code. Rust's expressiveness and the Rig framework make this possible. Let's start from the foundation and work our way up. Every Rust project starts with cargo toml. This is your project manifest. It defines dependencies, metadata, and build configuration. Let's break this down section by section. First, we have the package section with metadata. We set the name to iResearchAgent, version 0.1111 DEWA, and edition 2011. The edition is important. Rust editions introduce new features without breaking old code. Always use the latest edition for new projects. We also set the description, authors, license, and keywords. The keywords and categories matter if you publish to crates, PIO, they help people discover your crate. Now the dependencies. First and most importantly, Rig core. Rig is the framework that handles all the heavy lifting. It connects to LLM providers like Ollama, OpenAI, and Anthropic. It manages the context window and conversation history. It handles tool execution and the agentic loop, and it provides a clean, type-safe API. If you're coming from Python, think of rig as LangChain, but way faster, type-safe, and with Rust's memory safety guarantees. We're using version 0.27 with the derive feature enabled, which gives us derive macros for defining tools more easily. Next up is Tokio. AI agents are inherently asynchronous. Think about it. You send a request to the LLM, you wait. You search the web, you wait. You call an API, you wait. We don't want to block the thread during all this waiting. Tokio is Rust's most popular async runtime. We enabled the full feature which gives us multi-threaded runtime, the Tokio main macro, timers for delays and rate limiting, and synchronization primitives. This is non-negotiable for production Rust applications. Then we have SERD and SERD-JSON. LLMs speak text, tools speak JSON. SERD is the bridge. It converts Rust structs to JSON and back. With the derive feature, you just add serialize and deserialize attributes to your structs and SERD handles everything automatically. This is one of Rust's superpowers, zero-cost abstractions for serialization. For HTTP requests, we use request. It's built on Hyper and provides a high-level HTTP client. We use it for our web search tool. The JSON feature adds convenient methods for handling JSON in requests and responses. It handles connection pooling, HTTPS, timeouts, all the stuff you'd have to implement manually otherwise. For logging, we use tracing and tracing subscriber. And let me tell you, stop using println for debugging. Seriously. I see this all the time and it drives me crazy. In production, you want structured, async, aware logging. Tracing lets us see exactly what the agent is doing. Starting search, found 5 results, synthesizing answer. All with timestamps, log levels, and the ability to filter by module. This is how professionals debug. For error handling, we have 2 complementary crates, anyhow and this error. Anyhow is for application-level errors, great for the main function and CLI. It wraps any error with helpful context. This error is for library-level errors. It gives you derive macros to create custom error types with proper error messages. The combination gives you both flexibility and type safety. Use this error for your libraries, anyhow for your applications. Finally, for CLI and config, clap for command line argument parsing with derive macros, way cleaner than manual parsing. .env loads .env files, which is essential for local development. Async trait is required for async functions and traits. That's a current Rust limitation. And URL encoding handles URL encoding for search queries. That's our foundation. Now let's build on it. Hard-coding API keys or model names is a rookie mistake. We want our agent to be configurable without recompiling. Let's look at the config module. We define a config struct with 5 fields. Model is the Ollama model to use, like Llama 3.2 or DeepSeek. Ollama host is the server URL, defaulting to localhost on port 14034. Temperature controls response creativity 0 is deterministic, 1 is creative. Max search results limits how many results to analyze. And log level controls logging verbosity. This struct uses 2 derive macros, debug for printing with the debug format, and clone for creating deep copies when needed. Notice the pub keywords. In Rust, everything is private by default. Pub makes fields accessible outside the module. We implement the default trait to provide sensible defaults. If someone doesn't have a .env file, the agent still works. It defaults to Llama 3.2 as the model, localhost for Ollama, temperature 07 which is balanced between creativity and focus, 5 search results and info level logging. You can derive default automatically for simple cases. But implementing it manually gives you control over exactly what values make sense for your application. The fromEnv function loads configuration. First we call .env to load any .env file if it exists. Then we start with default values. Then we override with environment variables if they're set. We use the if-let-oak pattern here. This is a concise way to handle a single pattern match. If the environment variable exists, we use it. If not, we keep the default. For values that need parsing, like temperature, which is a floating point number, we use the parse method with the context method from anyhow. This adds helpful error messages. Instead of a generic parse error, users see temperature must be a valid floating point number. Much better user experience. I want to highlight the question mark operator because it's so important in Rust. It's syntactic sugar for error propagation. If the result is okay, it unwraps the value and continues. If it's an error, it returns early from the function with that error. This eliminates tons of boilerplate. Instead of writing match statements everywhere, you just add a question mark. It makes error handling both safe and ergonomic. Before we start the agent, we validate everything. The validate function checks that temperature is between 0 and 2, that we have at least one search result configured, and that the model name isn't empty. This is the fail fast pattern. It's much better to crash immediately with a clear error like invalid temperature 3x than to have the AI behave weirdly 10 minutes into a research task. Always validate your configuration at startup. We use anyhow's bail macro here. It creates an error and returns early. Very convenient for validation logic. Every module has tests. We define them in a tests module with the CFG test attribute, which means testing. It's not in your production binary. We test that default config has expected values. We test that valid config passes validation. We test that invalid temperature fails validation. We test that zero search results fails validation. Run these with cargo test. Rust's testing is built in, no external framework needed. Always write tests for your configuration logic. Now, technical part. Also the coolest. We're building the agent's hands. An agent without tools is just a chatbot. Tools let the AI interact with the real world. Our first tool is web search. Most search APIs like Google or Bing cost money. We're using DuckDuckGo because it's free and doesn't require API keys. First, error type, this error. We create an enum called search error with 4 variants. Search failed holds a string message for general failures. Rate limited indicates the search provider told us to slow down. No results holds the query that returned nothing. And network error wraps the underlying request error. Why custom errors instead of just strings? 3 reasons. First, the compiler checks that you handle all cases. Second, you can match on specific error types and handle them differently. Third, errors become self-documenting. The code tells you what can go wrong. The from attribute on network error enables automatic conversion from request errors to our search error. This is what makes the question mark operator work seamlessly across different error types. Next, results with 3 fields: title, URL, and snippet. Simple but important. This is the contract between our search implementation and the rest of the system. We derive serialize and deserialize for JSON conversion, clone for making copies, and debug for printing. Every struct that crosses boundaries, whether to JSON, to logs, or between modules, should have these derives. The is simple. It just holds max results as a configuration value. Notice this field isn't public. This is intentional encapsulation. Users create the tool through the new function and can't mess with internals directly. The new function is an associated function. It doesn't take self. It's Rust's constructor pattern called with web search tool : new. Is where the action happens. It logs the query, waits 500 milliseconds for rate limiting, calls the internal DuckDuckDuck method, logs whether results were found, and returns. That rate limiting sleep is important. It's respectful to DuckDuckGo and prevents us from getting blocked. In production, you'd want more sophisticated rate limiting with exponential backoff, but this is a good start. The async await pattern here is crucial. While we're sleeping or waiting for HTTP responses, Tokio can do other work. No wasted CPU cycles. This is what makes Rust so efficient for I/O-bound workloads like web requests. The DuckDuckGo holds an HTTP client with a 30-second timeout and a real user agent. Some sites block generic clients. We construct the URL with the encoded query and fetch the HTML endpoint. Why HTML scraping instead of an API? DuckDuckGo's API is limited and many crates for it are broken or outdated. Sometimes in Rust you just have to build it yourself. The HTML endpoint is free, reliable, and doesn't require authentication. We handle the response status explicitly. If we get a 49 too many requests, we return our rate-limited error. For other failures, we return search failed with the status code. This granular error handling lets callers decide how to respond, maybe retry for rate limiting, but fail immediately for other errors. The part gets messy, and that's real engineering. We have 3 different strategies to extract URLs from DuckDuckGo's HTML. Strategy 1 looks for the UJ parameter, which contains redirect URLs. Strategy 2 looks for the result_URL CSS class. Strategy 3 does direct URL extraction, finding any HTTPS URLs in the page. Why 3 strategies? Because DuckDuckGo's HTML isn't consistent. Sometimes results are in redirects, sometimes in CSS classes, sometimes just embedded in the page. Having multiple fallback strategies ensures robustness. We use a hash set to track seen URLs and prevent duplicates. We filter out DuckDuckGo's own URLs, tracking pixels, CSS files, JavaScript files, anything that's not an actual search result. This is the dirty work of engineering. The AI part is glamorous, but 90% of the job is reliable plumbing like this. Now our tool with Rig's agent system, we implement the tool trait for web search tool. The trait requires several things. A static NAMI constant that identifies the tool, type aliases for args, output, and error, a definition method that returns metadata, and a call method that executes the tool. Let me explain each piece. The returns a tool definition struct with the tool's name, description, and parameter schema. This is what the LLM sees. It tells the AI, hey, I have a tool called web search. It takes a query string. Use this when you need current information. The parameter schema is JSON schema format, the industry standard for describing data structures. We specify that query is a required string parameter with a helpful description. The AI reads this definition and decides it's on when to call the tool. That's the fundamental difference between an agent and a script. Scripts follow predetermined paths. Agents make decisions. The call first arguments and executes the search. It calls our search method, formats the results into a readable string, and returns. The formatting includes numbered results with title, URL, and snippet. We handle empty results gracefully with a helpful message instead of an error. All of this is type safe. The args type is automatically deserialized from JSON. The output type is automatically serialized back. The error type must implement the standard error trait. Rust's type system ensures we handle all cases correctly. Let me explain why this architecture is powerful. The tool knows nothing about the agent. The agent knows nothing about how the tool works internally. They communicate through a well-defined interface, the tool trait. This means you can swap implementations. Want to use Google instead of DuckDuckGo? Implement the same trait. Want to add caching? Wrap the tool in a caching layer. Want to add logging? Use a decorator pattern. This is the power of trait-based design in Rust. It enables composition, testing, and flexibility without inheritance hierarchies. Now, tool. Let's build the brain. This is where reasoning happens, where we wire everything together and let the AI make decisions. The most agent is the system prompt. This defines the agent's personality and behavior. Let me read you the key parts. You are a helpful AI research assistant. Your task is to research topics and provide summaries. Then the critical instructions: use the web search tool on Z to find relevant information. After getting search results, I immediately synthesize them into a summary. Do not make multiple search requests. One search is sufficient. This off the bat. Without these constraints, agents can spiral searching forever, never answering. They'll make 10 searches when one would suffice. They'll get stuck in loops. I've given specific instructions to prevent this. Use the tool once. Synthesize immediately. Don't keep searching. Be decisive. We also specify the output format, overview, key sources found, summary, and next steps. This gives the AI a template to follow, which produces more consistent, useful responses. The agent is clean. It holds the config and the search tool. The new function creates the agent and initializes the search tool with the configured max results. In Rust terms, the agent auto-ends its config and tools. When the agent is dropped, they are cleaned up automatically. No garbage collector needed. No memory leaks possible. The core. Let me walk through it step by step. First, we log that we're starting. Always log entry points, it helps with debugging. Next, we set the environment variable for Ollama's API base URL. Rig reads this to know where to connect. Then we create the Ollama client using rigs from env constructor. Now comes the beautiful part, building the agent with Rig's Fluent API. We call the agent with name. Then we chain preamble with our system prompt. Then we chain tool with our search tool. Finally, we call build to get the configured agent. This is the builder pattern. Each method returns a modified builder, allowing method chaining. It's fluent and readable. You can see at a glance what the agent is configured with. Then enhanced query that explicitly asks the AI to use the search tool and provide a comprehensive summary. We set multi-turn to 5, which allows up to 5 back and forth iterations for tool calls. And here's where the magic happens. Rig handles everything else. It's Ollama. Ollama reads the tool definitions and decides it needs to search. Rig intercepts the tool call, runs our Rust search function, gets the results. Rig feeds the results back to Llama. Llama generates the final synthesized answer. All that complexity, the conversation management, the tool execution loop, the JSON parsing, the error handling, hidden behind one prompt call. That's good API design. I also mode for need AI synthesis. You just want raw links fast. This method bypasses the LLM entirely. It calls the search tool directly, formats the results, and returns them. No waiting for AI processing. Instant results. It's a nice optimization for power users who know exactly what they're looking for and just want the links. Notice throughout. We use mapair to convert Rig's errors to anyhow errors with helpful context. Agent execution failed tells users what went wrong at a high level. We don't expose internal error details that would confuse users. We don't panic and crash. We propagate errors up with the question mark operator and let the CLI handle user-facing messages. This layered error handling, specific at the bottom, general at the top, is a production best practice. Finally, all together in RS. This is the entry point, how users interact with our agent. At the top, we have module documentation using the special .comment syntax. These comments show up in Cargo doc. They explain what the application does, list the features, and show quick start examples. Always document your public APIs. Future you will thank present you. And if you open source your work, good documentation is the difference between adoption and abandonment. We do by using derived macro. The arg struct has 4 fields. Query is the research topic, a required positional argument. Model is optional, overrides the environment variable. Quick is a Boolean flag for quick search mode. Verbose is a Boolean flag for debug logging. Inside stat of the small minutes, they're related internats way, to speak for internated status. The derived macro generates all the argument parsing, help text generation, version info, and error messages automatically. We add attributes to customize help messages, short flags, and environment variable fallbacks. The result is that users can run commands like cargo run -- rust 183 features -- quick or cargo run -- model deepseek AI trends 244 -- verbose, all automatically parsed and validated. Invalid input gets helpful error messages, -- help shows usage, clav handles everything. The Tokio main which transforms it into an async function by creating a runtime and running our code inside it. Without this, we couldn't use await. The function returns a result, which means it can fail. If it does, Rust prints the error and exits with a non-zero status code. The flowchart. CLI arguments. Initialize logging based on the verbose flag. Log that we're starting. Load configuration from environment. Override the model if specified on command line. Validate the configuration. Then create the research agent. Execute either quick search or full research based on the flag. Handle the result. The special. We don't just print stack traces. We print user-friendly messages. If the result is successful, we print a nice header, the results, and another header. Visual separation helps users parse the output. If there's an error, we log it for debugging, print a friendly message with an emoji, and then, this is key, we give actionable suggestions. If the error mentions connection refused, we suggest running Ollama serve. If it mentions model, we suggest pulling the model first. These contextual hints save users hours of debugging. Finally, we return the error to set a non-zero exit code. This is important for scripts and CI pipelines that check exit codes. The tracing subscriber builder. We disable thread names, file paths, and line numbers to keep output clean. Then we set this as the global default subscriber. Any tracing macro anywhere in the application will use these settings. This structured logging is invaluable for debugging. You can filter by level, grep for specific modules, correlate events by timestamp. So much better than printle and scatter throughout the code. Alright, now fire it up and see it in action. First, I have Ollama running in the background with DeepSeek version 3.2 loaded. Let me verify with Ollama list. Good, the model is there and ready. Now let's run a query about something recent, so we know it's not just training data the model memorized. Alt latest developments in Rust Async runtime 2024. Watch the logs as it runs. First we see info research agent, AI research agent starting up. Then info agent starting research task with our query. Then debug agent connected to Ollama on. Localhost with Llama 3 dies 2, then info agent configured. Executing research query. Now the interesting part, info tools, performing web search. See what happened? The LLM decided it needs to search. It formulated its own search query based on our request. Then debug tools fetching search results from DuckDuckGo. And info tools search completed, found 5 results. Now it's thinking. The LLM is synthesizing the search results into a coherent answer. And there, look at this output. We have a header line of equal signs, then research results, then another header. The overview section gives a brief introduction to the Rust Async ecosystem developments. The key sources found section lists the URLs we found, the official Rust blog, the Tokio website, various community blogs. The summary section synthesizes everything, discussing Tokio updates, Async's developments, new runtimes like Smol and Glomio. The next steps section suggests what to explore next, checking the Async working group. Following GitHub repositories. It ran locally, no API costs, complete privacy, about 15 seconds total. The search is fast. The LLM thinking is where the time goes. Now I'll type cargo run -- quick, Rust Web Frameworks 2024. This returns instantly, no LM processing, just raw search results. We see numbered results with titles and URLs, Arwobayet, Moiter-es, Actix-or-es, Axum documentation. When you just need links, this is the way. And that builds a complete production-ready AI research agent in Rust. Let's recap what we covered. Project structure with cargo toml and clean module organization. Agent configuration with environment variables and validation. Tool implementation for web search including custom HTML parsing when off-the-shelf solutions didn't work. Async workflows with Tokio and proper error handling with anyhow, thesaurus, and helpful user messages. Type-safe API integration with the rigframework. This isn't a toy project. This is real code you can extend and deploy. So, here are some ideas to extend this agent. Add a GitHub tool to search repositories and read code. Implement memory so the agent remembers past conversations. Rig supports this. Add a database tool to query your own data. Build a multi-agent system where one agent researches and another writes reports. Deploy it to production with Docker. The patterns you learned today apply to all of these. You've got the foundation. Now, what tool are you adding to your agent first? GitHub? Database? Something else? Let me know. Subscribe to the channel. I'm building more Rust AI content, multi-agent systems, local LMs, production deployments. You don't want to miss it. Join the Discord. Seriously, the community is amazing. Share your projects, ask questions, help others. Link is in the description. Support the work. If this tutorial saved you hours of research and helped you build something real, buy me a coffee. Every contribution funds more content like this. Link below. Grab the code. Full project is on GitHub at aiagent. Star the repo if you find it useful. Thanks. I'm done. Keep building, keep learning, and I'll see you in the next one. Now go write some Rust. Peace.